The first speaker would be Félix, who's live from, I don't know actually if you're in Paris or if you're in the UK.
No, I'm in Oxford.
Okay, you're in Oxford. Okay. So you will be the first speaker. So you got like 17 minutes and then we have some time for questions.
Perfect. Thank you, Arthur. And sorry for not being in person and for giving an online talk. So I'm currently doing a postdoc in Oxford, but last year I was in Montreal at the UQAM working with Arthur and Hélène Guérin on stochastic models, stochastic epidemic models, and that's what I'm going to be talking today. Okay, so just to give, okay, the slides are not, yeah, perfect. So just to give a bit of context for this work, so we started thinking about this project. It was like in September 2021, and as one speaker has already mentioned, it was the time where we were like discovering and being sure that actually the immunity was waning. And we were also speaking of like third doses of vaccine and fourth doses, etc., etc. So a very natural question at the time was, suppose that you have an infectious disease and that you have a vaccine for this disease, but that at the same time, the immunity which is induced either by the infection or by the vaccination is waning with time. The disease is transmissible enough, it can actually persist in the population, in which case we say that it reaches an endemic state. Okay, so that the disease is actually persisting in the population. But if you start vaccinating the individuals in a recurrent way, then you can somewhat increase the level of immunity of your population and at some point reach herd immunity, in which case the disease is not able anymore to transmit inside the population. And so what we wanted to study was this interplay between those two concepts. So like a way to put it is to say, like, if you have a vaccine and you are a policymaker, how frequently should you vaccinate the people in your population so as to prevent the disease from entering an endemic state? So the way we studied this question is by doing some modeling work. And so more specifically, so we studied a stochastic model. So I'm going to spend most of my time just describing the model, and so it's going to be very methodological, but I try to give some results in the end. Okay, so as I was saying, it's a stochastic model. So you have a closed population, so with a fixed number of individuals that we set to a parameter which is n. And in this population, we're going to track for each individual two quantities. So the first one, we call it the infectiousness. And the infectiousness of an individual is going to be the rate at which this individual is infecting other individuals in the population. So the second quantity is going to be what we call the susceptibility. And this is the probability that an individual, when entering in contact with someone who is infectious, gets reinfected. So somewhat what we had in mind was some sort of an intra-host model for like the interaction between the host and pathogen. But instead of giving a lot of details and modeling that explicitly, we took like a more phenomenological approach of just modeling infections and reinfections. Okay, so now let me describe exactly how we assign those two quantities to the individuals. So here what I'm representing is those two quantities for one individual, one focal individual in the population. Okay, so first, a good way that we like to explain the model is to start from a very simple situation, which is this SIRS model. So in the SIRS model, what you do is that when an individual gets infected, it enters a first state, which we call infectious, and during which this individual can infect other people. And in our framework, what we do is that we set the infectiousness of this individual to a constant value. After some random time, which is denoted by TI in our model, then this individual stops being infectious. And in the SIRS model, it enters a state which is the recovered state. And in that state, it cannot infect any more individuals, but also the individual is assumed to be immune to the disease, and so it cannot get reinfected. And in our context, this means that we set the infectiousness of the individual to 0, which means that this individual cannot infect anymore, but we keep the susceptibility of the individual to 0 also. And this means that if during this period of time the individual encounters someone who is infectious, it's not going to be reinfected. And so the last ingredient of this SIRS model is that there is a waning of the immunity, and that after some time, which we call TR here, and which is just an exponential distribution, the individual becomes susceptible again, and we model that by saying that the susceptibility is set to 1. Okay, so this is not the model that we're considering. It's just an example of the type of dynamics that we're considering. Actually, what we do is that we do something a bit more general. So instead of thinking of the infectiousness and the susceptibility as being like some discrete quantity, we just think that they are quite a general, continuous quantities. And so the real model that we're considering is that upon infection, the individual is sampling a random infectiousness curve. In the case of the SRS model, this was just a constant function, but now it can be any random function. And we just think of it as being like some bell-shaped function to represent that there is an exposed phase and a lack of infectiousness in the end. And so after a random time, which is dependent on this function, then the individual recovers and we set its infectiousness to 0. And then instead of having like a jump function for the susceptibility, what we do is that we suppose that upon recovery, an individual samples again a random function which is non-decreasing and which gives its susceptibility. Okay, so after some time, the individual gets reinfected and we start again this loop independently, and we do so independently for each individual in the population. So this is the dynamics of our model without vaccination. And so the way that we incorporated vaccination in this picture is by saying that when an individual gets vaccinated, for instance, at this time, well, then we reset its susceptibility. So somewhat vaccination resets the immune system of the individual. It's quite a strong assumption, but that's how we do it. And so when does an individual get vaccinated? Well, upon being recovered, an individual is going to sample the time at which it should get reinfected, always according to the same distribution that we denote by TV. And if this individual doesn't get reinfected before it gets vaccinated, then it gets vaccinated and we reset its susceptibility. And at this moment, it also resamples the time for next vaccination, okay, which is this arrow, and we restart the dynamics afresh. And so in this case, the individual gets reinfected before it gets vaccinated, and then we restart an infectious cycle. And this is the dynamics that we do at the individual level. Okay, so I won't have time to spend more time on this explanation, but just maybe to summarize, we've got 4 main ingredients in the model. The first one is that there is a population size. The second is that there is a random quantity, which is the random red function. And the parameter is the distribution of that function, which we call the infectiousness curve. There is a second function, which was like this blue function. And again, the parameter is the distribution of this random function, which is sigma. And the last one is the distribution of the period of time between 2 vaccinations of the same individual. And just if you want those 2 quantities, we think of them as being fixed by the biology of the disease. Okay, it's really like this interaction between the host and the pathogen, which will tell you somewhat what's your viral load and what's your level of antibodies or T cells, CD8 plus T cells, if you want. And this quantity, we really think of it as being like the policy, the vaccination policy. So you are a government, say, and you can say to your citizens, okay, you should get a vaccine dose somewhat between 5 months and 8 months before the last dose or before the last positive test that you had. So really think of this TV as quantifying this effect. Okay, so first thing we've done when we've got this model is just some simulation. So I'm not showing all of the parameters, but these are like 3 independent realizations of the model. And you see that for this parameter set, well, it seems that the disease reaches some sort of a plateau, some sort of an equilibrium. And this is what we have in mind for what we will call an endemic state. It's the situation where like the disease seems to be able to persist in time. Sorry, this is representing the fraction of infected individuals in the population through time. So now I'm just going to change one parameter, which is that I'm going to decrease the typical time between the vaccination between 2 vaccinations in the population. And you see that this completely changes the qualitative picture that we have, and that now the disease is actually dying out. Okay. And so this is the kind of transition that we wanted to study. Okay. So like for what parameter values for this quantity TV do you go from this situation, which is the situation that we would ideally want, to this situation, which is the situation where you see an endemic equilibrium. Okay, so the problem is that this stochastic model is individual-based. It has a lot of parameters. And so basically, there is nothing that we can tell analytically about this model for a fixed n. But however, if we let the size of the population goes to infinity, there is some sort of a law of large numbers going on. And you see on this simulation, I've multiplied the population size by 10. And you see that now the picture looks much less noisy. We've really diminished, if you want, like the noisiness of the picture. And I couldn't simulate more than 10,000 in a reasonable time. But if you let the number of individuals go to infinity, we can actually prove, we've not done it, but could prove that the system converges to a deterministic curve, which corresponds to the law of large number limit of the process. And it's this deterministic curve that we are going to study as an approximation of our stochastic model. Okay, so we've not proved rigorously that the system was converging to this black curve, but we are still able to say what should be these deterministic limits. So these are the equations which are fulfilled by the limits, so don't look at them too much. I won't have time to go through the details, but I just want to make 2 points with those equations. The first one is that this is a partial differential equation, and this is not an ordinary system of ordinary differential equations. And the reason for that is that at the microscopic level, at the level of the individuals, we have a system which is called non-Markovian. This means that if you want the waiting times at the microscopic level are general, they are not necessarily exponentially distributed. And this means that your population is not well described by just counting the number of individuals in each compartment. You need to retain, if you want, a bit more information. And this is my second point I want to make. This is that the only, if you want, a relevant way of describing the population in this context is by looking at what we call the class age structure of the population. And in this context, age is not the physical age, like the calendar age. It's the time which is elapsed since the last infection or the last vaccination. Okay, maybe you've already seen that this is actually the model from Kermack and McKendrick. There are like those 3 papers, really fundamental papers. And this is actually a variation of the model of the paper number 2 and number 3. Okay, so now we can rephrase our question of when does the population reach endemicity? When does actually the vaccination campaign manages to prevent endemicity, as studying the equilibria of this system of PDE. Okay, so what we want to understand is for what region of the parameters do we see an endemic equilibrium, and for what region do we not see an endemic equilibrium? Okay, and in that case, and this is typically the region we are aiming for. So what we are looking for now are stationary solutions of this PDE, so solutions that do not depend on time. So you can do some computation, and you can actually prove that there is always some sort of a trivial equilibrium, which in this context we call the disease-free equilibrium. And so this is an equilibrium where you see no infected individuals. So the function I, given like the density of infected, is the null function. And when there is no infected in the population, there is only one dynamics actually, which is the vaccination. And it's just that individuals get vaccinated recurrently according to a renewal process with distribution T sub V. And so there is still something which is going on, which is that you are still building some sort of immunity in the population due to vaccination. And we can quantify this immunity through a very important quantity in our model, which we call the average susceptibility at the disease-free equilibrium, and which we denote as sigma. And this is really like if there were no infected individuals in the model, and you were just like picking one individual from the population, what's the susceptibility that you see? Well, on average, this is going to be sigma. So it's really quantifying how effective your vaccination is. Okay, so now there is always a disease-free equilibrium, but somewhat this is not the equilibrium that we're interested in. What we're really interested in are the endemic equilibria, for which, the function I is not identically 0. And so what we were able to show, but we've not proved it, once again, we have to use like some heuristic arguments because the system is really complicated. But it seems that there can exist an endemic equilibrium if and only if this condition here is fulfilled. So this sigma is the susceptibility at the disease-free equilibrium, which I was showing you on the previous slides, and R0 is just like the usual basic reproduction number. And in our model, it takes the following expression. So, okay, if some of you knows a bit about branching processes, next generation matrices, okay, this might seem familiar, and there is actually a next generation argument motivating these results. Okay, and so Okay, so there is not always an endemic equilibrium. And so a nice way to illustrate the asymptotic behavior, if you want, of the system is to sorry, there is a bit of noise in the background. Could you please turn off the microphone? So a good way to summarize, if you want, the asymptotic behavior of a system is to draw what we call the bifurcation diagram. So what I've done here is that I fixed every parameter in the system and I'm increasing R0 from 2 to 6. And the red line is the limit, if you want, of this system. And so you see that below this dashed line, well, the system is converging to an equilibrium where there is no infected individuals in the limit. And after this red line, there is a bifurcation and your system is actually reaching an endemic equilibrium. And this dashed line that I have represented is exactly this criterion here. It's like this 1/sigma. So it seems to be really the right criterion. Okay, and so I think that's about all what I wanted to say in my time. So just to make a quick wrap up, what we've done, so it's still a bit work in progress. We've not submitted anything so far. We're in the process of finishing this project. So what we did is that we introduced a new stochastic epidemic model, which is individual based, and maybe the main features are that the immunity in the system is waning, that we've incorporated vaccination in a recurrent way, and compared to like more usual approaches in epidemic modeling, we've used a non-Markovian model. And this is quite interesting. So then what we're able to do is to derive the large population size limit of our model, and it becomes a nonlinear PD due to this non-Markovianity. So we've shown that the endemicity is possible if only if there is this very simple criterion which is fulfilled, which is that R0 times sigma is greater than 1. And lastly, really part of the work that I didn't have time to present is that now you can think of this sigma as quantifying the efficiency of a vaccination policy, because if one vaccination policy has a higher sigma, this means that it's better at preventing an endemic equilibrium. And so a completely different and more applied part of our work was now to use sigma as an indicator of a nice vaccination policy and to try to study some more public health applications. Like if you have several groups, how do you all allocate vaccines in an optimal way between them? What if like there is some vaccine hesitancy? How should you choose exactly the duration of your vaccine to have the optimal impact and this kind of things? Okay, so I think that's all for me today. And so thanks for your attention, and I'll be happy to take questions.
Thank you. Okay. Oh, so we got, I don't know what's in the chat. No, it's just chatting. Okay. So I don't know if there are questions from the audience. Okay, okay, there is one. Do you want to, maybe I can give you the mic, but you cannot hear.
Yeah, I'm sorry, I cannot hear unless...
Yeah, my name is Yogita, and I'm talking. So I'm just curious about the method you are using for the PDs, like to find the stationary solutions and so which method you used basically for the PDs?
Yeah.
What are the boundary conditions and restrictions?
Yeah. Okay. So to simulate it, actually, we cheat a little bit if you want, because you see it's a transport PD. So what we do is that we use some sort of a method of characteristic to transform this PD into a Volterra equation, and we actually simulate the Volterra equation rather than the PD. This is like for the numerical part, and for the analytical part, just you see that if you set T, if T is not, if the solution does not depend on T, these two derivatives, they disappear, and all you get is just an ordinary differential equation for your age structure in the. I mean, it's just it becomes an ordinary differential equation because you are looking for a stationary solution. And this ordinary differential equation, we can solve it. Okay, it's not very explicit, but we can solve it in terms of the parameters. And this gives us like some sort of a fixed point equation that we need to solve if we want to find an endemic equilibrium. And then we can just do some math. And this is the criterion which is showing up.
Okay, thank you.
Thanks.
Thanks a lot.